In this video, I'm going to go over phase plane and non-dimensionalization and phase plane for the Michaelis-Menten Kinetics system of equations. So just for a little bit of language, the S equation here describes the concentration of the substrate. This is a molecule that is going to be, in some sense, processed by an enzyme, and that's the E equation. So this is the concentration of the enzyme. And E tot minus E, which is in the original version that I gave you in class, I think I called that C. That is the complex, which is S and E together. So that's just a little bit of language in case I use that while I'm going through this problem. Okay, so first step here is to non-dimensionalize. So just looking quickly, I won't go through a full listing of all the scales, but you'll notice that we have a time scale here. That's K2 has units of 1 over time. K3 will also have units of 1 over time. And K1 has units. Now you'll notice that in this equation here, we have K1 will have to have units of 1 over enzyme concentration time because it needs to cancel the enzyme units here. But in the next equation down here, I need to have, K1 has to have units of concentration of substrate, 1 over concentration of substrate, and also time in the denominator of that one as well. And so what that means is that K1 simultaneously has to have both units, and that's because these two are E and S represent concentrations of molecules that are undergoing a reaction, and the stoichiometry is 1 to 1. So that means that we should really be scaling S and E with the same scale, and that way we can make sense of this K1 simultaneously having two different types of units, which it won't if we keep the enzyme concentration scale and the S substrate concentration scale the same. Okay, so I have basically two choices for time scales, these two, or well, three, I guess. It could be K2, K3, or K2 plus K3. And so I will, let's see, which one do I want to do? The sum of 2 is a little bit unusual, so let's not do that. And so let's do K2 as our time scale. So tau is equal to KT times T. And then S, so now we have to find something that has units with concentration in them, and that's definitely K1 is the only thing around. Oh no, there's also E tot. Yes, so for reasons that I will talk about later in the course, I'm actually going to choose E tot as the scale for both S and E. So I'm going to redefine S to be E tot. Well, I should say this a different way. I'm going to define a new variable X to be S over E tot so that I can replace all appearances of S by E tot times X. And remember that S is going to be a function of T and X is going to be a function of tau, and I'll leave out the details of that just to save some space and time. Okay, so E is going to similarly be E tot times Y. So I'm defining this new non-dimensional enzyme concentration Y, which will be E over E tot. So let's put all that together into the equation. So we end up with K2 multiplying a dd tau of, and now in place of S, we get X, but I have to put an E tot out in front. And then that is equal to minus K1, and now I'm going to get an E tot squared, one from the S and one from the E, times XY, plus K2, and I'm going to factor out an E tot from the brackets, and that becomes a 1 because that was E tot before, minus, and E became E tot times X, so this is going to just be X left in the brackets. And then in the second equation, we're going to have K2, the time constant, 1 over the time constant, which pops out into the numerator, and we have E tot multiplying dy d tau. And that's going to be equal to, I have the same term here, so this is going to be E tot squared times xy, and plus K2 plus K3, and here I also have E tot factor it out of the brackets, and in the brackets 1 minus, oh, whoops, x, that's not x, that's y. So that's a y there and a y there. So let's fix those, y and y. Okay, so the e's, y, y. Yep, okay. So now what common terms do we have? You'll notice there's an e-tote common to all of these terms, and I have a K2 common here and there, but I have none there, so I have to put it in the denominator. And then here I have an e-tote, and then cancel that one and one there. And then I have a K2. Well, I won't divide that. I'll leave that because there's no nice cancellation, or very little nice cancellation. Okay, so now I'm going to get x dot, replacing the dd tau by a dot, equal minus K1 e tote divided by K2. And you'll notice this is a non-dimensional quantity because K1 had units of 1 over time, 1 over concentration, and K2 has units of 1 over time. So the times cancel, and the e-tote multiplying the K1 cancels the e-tote, the concentration units. So that's no dimensions. And then I have an xy plus, now the K2 is gone, and I just have 1 minus y. And in the y equation, I have, again, that minus K1 e tote. And when I divide through by this K2 here, I get a K2 in the denominator. So that's the same non-dimensional term in front. And then I have an xy plus, and now when I divide through by K2, I get 1 plus K3 over K2. And that's a non-dimensional combination of parameters there, and then that's multiplied by 1 minus y. So let me rewrite that in terms of simpler parameters. So let's call this minus, I'll call this alpha times xy plus 1 minus y, and x dot, sorry, y dot is equal to minus alpha xy plus 1 plus beta times 1 minus y. All right, so we've gone from having 1, 2, 3, 4 parameters in the problem down to 2. 1, 2, down to 2? Oh yeah, down to 2, because we were locking the scales for S and E together, so we couldn't reduce a parameter for each of those. Okay, so now we have the phase plane question to answer. And there we're going to find the nullclines. So let's find the x dot equals 0. That happens when minus alpha xy plus 1 minus y is equal to 0. So we solve for y, and we get 1 equal alpha x y plus y, and then factor out a y from that, and I get y equal 1 over 1 plus alpha x. So that's the x dot, the x nullcline, and the y nullcline is going to be something similar. So now I'm going to have minus alpha x y plus 1 plus beta 1 minus y equals 0. And so let's divide through by a 1 plus beta. And now I get the equation minus alpha over 1 plus beta times xy plus 1 minus y is equal to 0. And you'll notice this is pretty much the same as this equation here, except alpha is replaced by alpha over 1 plus beta. So I can just write down that the y nullcline is going to be 1 over 1 plus alpha over 1 plus beta times x. Okay, so just a reminder here, I think I didn't explicitly state it or list it out, but alpha is K1 e tote over K2, and beta is K3 over K2. Now, those will certainly be positive because the rate constants K1, 2, 3 are all positive, as is the concentration E tote. So we know that alpha is going to be bigger than alpha over 1 plus beta, because if beta is positive, I'm dividing alpha by a number greater than 1. So what that means is when I go to draw the phase plane, I have x down here and a y up here, and let's draw the x dot nullcline in green. And so that's going to start at 1 up here, because when x is equal to 0, y is equal to 1. And then it's going to decay away to 0, like a 1 over x function. And then in orange, let's do the y nullcline. Now, this one is pretty much the same function, except the decay is, so this is a smaller number, which means we need a larger value of x to get to the same value of y as we did for the green curve. So that means that this curve is going to be at a lower angle and eventually converges also to 0. So how do we cross those? So we know that we cross the green nullcline vertically because x dot is 0, so there's no change in the x value along the green line. And then we cross the orange line, or orange curve, horizontally because that's a y dot equals 0. So now let's try and fill in some directions here. So let's just let's see what happens along the x and y axes. If so we go back to here, the equations. If x is equal to 0, that means we're right along this y-axis here. Then we get that x dot is equal to, this term will be 0, and we'll have a y minus 1. Oh, now this point here is at 1. And so y minus 1 everywhere throughout here is going to be positive. So that means that x dot will be 0 plus a positive number. And so the x component is going to be increasing as I cross that line. And the y component will have this part equal 0. And 1 minus y is still positive. And we're going to have, now the y component is going to be, instead of having y minus 1, it's 1 plus beta times y minus 1. So it's going to have a larger component in the vertical direction. So we're going to cross the y-axis always with a slope of 1 plus beta, which is greater than 1. So it's always coming in like that. And along the x-axis, we have y equals 0. So there we have just, this will be 0 and this will be 0. So we're just left with 1 in the x component. And in the y component, we have y is equal to 0 here, y is equal to 0 there. So we have a vector 1 plus beta. So same slope, but maybe the amplitude, the size of that vector is going to be different. Okay, so clearly we're going to be going up and over in this region here. And then as we cross the green nullcline, so because this was a simple root at the nullcline, in other words, the factors in this equation did not have multiplicity 2. We know that we're going to switch signs, so the horizontal component is going to shrink down to 0, and then on the other side it's going to point in the opposite direction, but the vertical component is not going to change. So let me find a spacious point in here. So that's going to face in this direction, and this one's going to face in the vertical. And then as I cross the orange nullcline, so these guys, actually we can fill these in, and these ones, and these ones. And then as we cross vertically, we're going to have a 0 component, and then it's going to flip to be negative. Okay, and the crossing of, so if we wanted to include this beyond, this would go off in this direction, and they would swap orders. Because the green one goes to an asymptote at minus alpha, and the orange one goes to an asymptote, no, at 1 over alpha, minus 1 over alpha, and the other one goes to an asymptote at minus 1 plus beta over alpha. So the orange one has an asymptote further back, so it'll be lower. So what we have then is one steady state right there. And you can see what happens if you start up here. You might come directly down into the steady state. But if you start anywhere further out here, let's say, then you'd be coming down and you'd have to cross horizontally, and then you can't get out of this region. So everything in this region is trapped in this region and has to head up to the steady state. And so whenever you see that happening, you know that you have to have a stable steady state, because there's a whole open area that converges into the steady state. And the only type of steady state that does that, especially with a trap, like a little triangular trap in which they get funneled, that can't be a spiral because you can't spin around it and escape the orange-green wedge. And you have to have lots of solutions heading in. Certainly a saddle wouldn't be able to escape out of that region. And so we know we have a stable node. And all these solutions get funneled in to here. And that is as much detail as I am going to include in this phase plane.